In this video, we will learn about electromagnetic induction. So, EMI, that is electromagnetic induction, is a phenomenon of production of an induced EMF or current in a coil placed in a region where the magnetic field changes with time. This phenomenon of electromagnetic induction was discovered by Michael Faraday in 1831. Now, the experimental demonstration of EMI phenomena. So we take a coil AB of insulated copper wires having a large number of turns and connect the ends of the coil AB to a galvanometer G. Okay. Now we take a strong bar magnet NS and quickly move its north pole towards the end A, as shown in the figure. Now we observe that the galvanometer pointer shows a momentary deflection in one direction, say right direction. Now the momentary deflection shows that a current has been induced in the coil, and the deflection becomes zero as soon as the motion of the magnet stops. Now we move the magnet NS away from the coil AB, like this, with its north pole still facing the end A, right? Now we observe that the galvanometer showing a momentary deflection in the direction opposite to the first, say left. Now the deflection is towards left. Now it means that the induced current is set up in the direction opposite to the first one. Thirdly, we obtain similar result, that is deflection towards the right in a galvanometer as in A. But if we keep the magnet NS at a fixed point and move the end A of the coil AB towards the north pole of the magnet, again the galvanometer pointer shows momentary deflection towards left if the coil AB is moved away from the north pole of the magnet NS. Okay. Now, when both the magnet and the coil are kept stationary with respect to each other, the deflection in the galvanometer is zero. It shows that no induced current is set up in the coil when there is no relative motion between the coil and the magnet. Lastly, if steps A and B are repeated with the south pole S of the magnet NS facing the end A of the coil, we obtain the deflection in the galvanometer pointer again. However, the direction of deflection of galvanometer would be just opposite to that with the north pole facing the end A of coil AB. Now, what is the explanation of the experimental observation we see? See, from the above mentioned experiment, it can be concluded that the motion of the magnet relative to the coil produces an induced EMF across its end, and as a result, an induced current is set up in the circuit. Now, when the magnet is brought nearer to the coil, a great number of magnetic field line passes through the coil. So the magnetic field around the coil increases. This increase in magnetic field induces an EMF across the end of the coil and an induced current begins to flow in the circuit. Now when the magnet is moved away from the coil, the magnetic field around the coil decreases. And this decrease in the magnetic field line induces an EMF across the ends of the coil, and consequently an induced current is again set up in the circuit. Now when the magnet is stationary relative to the coil, the magnetic field around the coil is constant. As there is no change in the magnetic field around the coil, so no EMF is set up across the coil and hence no induced current flows through the circuit. Now, what is the magnitude of the induced current? So the magnitude of the induced current depends on the following three factors. First is the strength of the magnet. If the magnet being moved towards or away from the closed coil is a stronger one, the induced current produced in the coil will be more. So magnetic field more, the strength of the magnet more, the induced current will be more, right? Secondly, if the number of turns in the coil, that is N, are increased, then the magnitude of induced current will also be increased. Thirdly, if the speed of the movement of the magnet, that is, if a magnet is moved quickly, the magnitude of induced current is large. For slow movement of magnet, the current induced in the closed coil is much less. Now, about the direction of induced current, we use Lenz law. So, the direction of induced current can be obtained by applying the Lenz law. Lenz law states that the direction of flow of induced current is such so as to oppose the change in the magnetic field responsible for the production of induced current. Okay. Now, what is the illustration of this Lenz law? So, in figure, you can see that the north pole of the magnet NS, when brought nearer to the coil AB, the magnetic field increases. Hence, an induced current flows in an anti-clockwise direction when seen from the neighboring side AB of the coil. Now, due to this anti-clockwise induced current, the end A of the coil develops north polarity, okay, and opposes the motion of the magnet towards the coil. Now, when the north pole of the magnet Ns is moved away from the coil AB, the induced current flows in clockwise direction when seen from the side end A of the coil. As a result, the end A develops south polarity and opposes the motion of the magnet Ns away from the coil. Okay, I hope this topic is clear to you. Thank you.